Hi, Math 30-1s. Today we're going to take a look at applications in finance and how that relates to exponential and log functions. So at the top of the page, it discusses investing money. Now, when we invest money, the two basic types or ways that we're going to be talking about investing money and the money that is calculated when we invest it, are simple interest and compound interest. Okay, we're going to compare the two types of interest. Now, when we talk about simple interest, what you're going to see is that it creates a linear function. Okay, so something similar to what you did in Math 10. Okay, when you graph the data points, it will give you a line. When we talk about compound interest, you will see that it gives you an exponential function, okay, or an exponential graph, and that's what we're really interested in. So even though we're not really discussing linear functions in this chapter, we want to compare the two types of interest, but the major focus will be on the compound interest and the exponential functions that are created from those situations. Okay, so just to start, we take a look at simple interest. So it says simple interest is usually applicable to short-term investments of 1 year or less, or to longer-term investments where the annual interest is paid to the investor and not reinvested. So for example, if you were to invest $500, which earns interest at a rate of 6% per year, how much interest would you earn in 1 year? Well, in 1 year, what you would do is you would take the initial amount of money, which is the $500, okay, and you would multiply it by the interest that you are given for that 1 year, which is 6%. So 500 times 0.06, that's going to be $30. So in 1 year, you earn $30. Now, in half a year, okay, what would you do? Well, in half a year, you would figure out, okay, again, what amount of money did I start with? I would multiply it by, okay, the percentage rate that's given for the full year, but we're talking about half a year, so I'm either going to multiply that 0.06 by 1/2 or divide the interest by 2. Okay, they're not going to give you 6% for half the year, they're giving you 6% for the full year. So if you're only going to calculate how much interest you're getting in half a year, you have to cut that calculation in half. So that will work out to be $15. Okay, and then similarly, if we're going to discuss how to calculate the interest for 1 month, I would take the initial amount again, $500. My interest rate is 6% for the year, but 1 month, okay, I'm going to divide it by 12 because there are obviously 12 months in the year, and that will work out to be $2.50. And again, those amounts are just the interest that you have occurred, okay, in that time period. Now, in general, it says part B, if R now is the annual interest rate expressed as a decimal and P dollars is the initial investment, calculate how much interest you would earn in 1 year. So same basic idea, P is the initial investment, you're going to multiply it by the interest rate as a decimal. Same thing you did up above. The 500 was your initial investment, and there was your interest rate, okay, as a decimal, 6% written as a decimal. In half a year, same thing as up above, P times the interest rate and then divided by 2 or multiply by 1/2. And then for T years, it would be the amount that you started with times the interest rate, and then T represents the number of years. So it could be 3 years, you'd put 3 in for T, 10 years, you'd put 10 in for T. Okay, so just a general equation there that would help us calculate the annual interest, okay, or the interest for the time period that is in question in that particular instance. So it says the formula that we use to calculate simple interest is given as the following. Okay, I is equal to PRT. Okay, I stands for interest. P is the principal amount, or what you start with. R is your interest rate as a decimal, and T is your time in years for which the money is invested. Okay, and that's what all of the variables on the side here, okay, are also indicating to you. So as a calculation or some warm-up questions that deal with simple interest, let's read class example 1, where it reads, Millie invests $2,350 at 7% per year for 6 months. Calculate after the 6 months the simple interest on Millie's investment. So they just want the interest. So I is equal to P times R times T. So the interest will be equal to her initial amount, $2,350, times the interest rate, 0.07, and then 6 months, which is half of a year. So you can write 1/2 there, you can write 0.5, whatever you understand or prefer to write in the brackets there. The calculation will be the same, and that comes out to be $82.25. So that's just the amount of interest. So now they want to know the value, okay, of her, I apologize. Okay, they want to know the value of her investment. So if I want to calculate the total value of her investment, I would add the initial amount that she started with, okay, plus the interest that she accumulated in part A of the question. So plus the interest, which was $82.25, okay, and those two together, okay, $2,432.25. Okay, so there is the total value of her investment now, what she started with plus the interest that she earned. Okay, so very quick warm up on what simple interest is. So now we get into compound interest, which I mentioned at the beginning of the lesson is what we're really kind of interested in because it creates an exponential curve, okay, or it is an exponential function when we look at the equation. So it reads like this: in simple interest, the principal at the beginning of the year is the second year, is the same as the principal at the beginning of the first year. In compound interest, however, the interest earned during the first year, okay, is added to the original principal to form a new principal. So to understand the comparison between the two, that's what we're going to do on the next couple pages. Okay, take a look at how they are different and what they look like when we graph them. Okay, so here we go. Exploring simple interest and compound interest. It says a bank offers two types of savings bonds. Okay, a regular savings bond, which pays simple interest at 9% PA. Now, PA, when you see that written in a question, stands for per annum. And per annum is the same thing as per year. So when you see that, you just think, oh, okay, 9% per year. That's what I'm being given by the bank. Compound interest, or compound savings bond, which pays 9% also per annum, compounded annually. So let's take a look at the simple interest first, okay? And that's what they are going to start with right here. So it says the simple interest. The simple interest each year is 9% of $5,000. So to calculate that, again, you would write 9% as a decimal and multiply that by the $5,000, and that will give you $450. So that's the amount of interest you're going to get every year, and that's what you'll notice here on the chart. Okay, when I go from year 1 to year 2, I am adding $450, and that's going to be the case when you go from one year to the next, the whole way down. Okay, you are continuously adding $450. Okay, and that's what we mentioned on the first page, is that amount of interest does not change from year to year. Okay, that interest is calculated on the initial amount and never changes. So what we're doing going from year to year is just continuously adding $450. So when I do that, you can see I now have $5,900 after year 2, or at the end of year 2. At the end of year 3, I will therefore have $6,350. At the end of year 4, $6,800. At the end of year 5, $7,250. $7,700 at the end of year 6. Year 7, I will have $8,150, and finally at the end of year 8, $8,600. Okay, so I'll just go etc. like this all the way down. Okay, I'm continuously adding $450 every year, and that's basically simple interest. That's the way it works. Now, when I talk about compound interest, okay, this is going to be a little more complicated and a little more involved in the calculation. This is the way it works. At the end of year 1, what's going to happen is this. I'm going to take the principal, which in this case is the $5,000, and to that, I am going to add the interest. Now, here's the interest calculation. 9% of $5,000. So that's how I get the interest. 9% of 5,000. So what you'll see in that calculation is I have two terms, okay? Here is one term, and here is another term. Now, what's common between those two terms is this 5,000, so I factor it out. If I factor out the 5,000 from those two terms, what I'm left with is 1 plus 0.09, which gives me 1.09. So at the end, this is an expression for how much money I have at the end of year 1. Now, what they don't write in there, and what I'll show you right now, is at the end of year 1, there is an exponent here, okay, which is also a 1. And if I use that same rationale moving forward, you'll see that at the end of the year 2, Okay, I'm going to have a 2 here. And okay, at the end of year 3, I'm most likely going to have an exponent of 3 down here, okay, which I will work towards. But if I go back to year 2 now, what you'll notice is that the amount at the end of year 1 becomes the principal, okay, at the beginning of year 2. So that 5,000, 1.09 to the exponent of 1 is now my principal. Then I have to add the interest to that amount. So here's the principal, and here's me calculating the interest on it, 9% of that amount. Again, I have 2 terms. I factor out what's common, which is the 5,000, 1.09. That's what's common to both those terms. I'm again left with 1 plus 0.09, which is another 1.09. Now I have 2 of those, so it's 1.09 to the exponent of 2. Okay, as I move into year 3, this amount here is now going to be the principal that I start with, okay, at the beginning of year 3. So 5,000, 1.09 to the exponent of 2 is the principal. To that, I have to add the interest. So how do I get interest? I take the principal amount and I multiply it by 9%, and that will give me the interest on that amount. Again, just like as I did in the first 2 years, I have 2 terms, 1 term and 2 terms. Okay, what is common to those 2 terms is 5,000, 1.09 squared. So I factor that out. And what's left when I factor that out from those 2 terms is 1 plus 0.09. Okay, so I have this 5,000, 1.09 squared, and then another 1.09 now when I add the 1 to the 0.09. So as a simplified expression at the end of year 3, it's 5,000, 1.09, and like I had said, to the exponent of 3, okay, which matches the year at the end of the year. So those are all just expressions. What you're really interested in are the end expressions, so the ones with the check marks that I have there. That's what I really want to focus on moving forward, because as we take a look at the chart on the next page, that's what we are going to be coming up with for the value of the bond and the final amount. So again, for year 1, it's 5,000, 1.09 to the exponent of 1. So that's obviously 5,450. Now, at the end of year 2, okay, again, year 2, 1.09 squared. What you want to make sure you do is you do this calculation first. Okay, you want to go 1.09 to the exponent of 2 first, and then take that value and then multiply by 5,000, okay? The reason being is that exponent of 2 only belongs to the 1.09. So I want to go 1.09 to the exponent of 2, take that value, and then multiply by 5,000. Okay, so when I get that final amount, it's $5,490.50. Okay, now I go to year 3. So year 3 will be an expression of 5,000, 1.09 to the exponent of 3. So again, when I do this calculation, 1.09 to the exponent of 3 first, then multiply that by 5,000, and I will get $6,475.15. Okay, moving on to year 4. Okay, the expression in year 4 will be 5,000, 1.09 to the exponent of 4. So again, 1.09 to the exponent of 4 times 5,000. Okay, so that's $7,057.91. Okay, so we just keep going here. Year 5, 5,000, 1.09 to the exponent of 5. Okay, so 1.09 to the exponent of 5 times 5,000. Okay, so that's $7,693.12. Okay, year 6, 5,000, 1.09 to the exponent of 6. Okay, and that will yield $8,385.50. Okay, year 7. Okay, 5,000, 1.09 to the exponent of 7. Okay, and that'll be $9,140.20. Year 8. Okay, we're just about done. 5,000, 1.09 to the exponent of 8. Okay, and that will give you $9,962.80. 81 cents, okay? And then just as a general case, all right, if the year was N, okay, what I would have is 5,000, 1.09 to the exponent of N, okay? And that's what they write here. The value at the end of N years is that same expression that I just came up with. So after all this comparison between simple and compound interest, here's what they really kind of want us to understand and study moving forward. So it says, in general, if A is the final amount, P is the initial principal, I is the annual interest rate, and N is the number of years, we're going to have this formula. A is equal to P, 1 plus I to the exponent of N. Okay, so that is going to be our interest formula, okay, when we are talking or discussing compound interest. Okay, that is something that we are going to want to know moving forward. Okay, that formula, you need to know it. So highlight it, start like I did there, okay, and make sure you make special note of it. Now, as you will see moving forward here, that equation, even though it looks a little different, is really just the exponential equation, okay? This is like your y, so y is equal to, P is like your a, 1 plus I is basically the b value, and N is like your x. So it does take on the form of an exponential equation, which is y is equal to a times b to the exponent of x, okay, which we've seen in this chapter and the previous one. So when I graph compound interest, it does create an exponential curve, and we're going to see that right now. So in part F, it says plot the data from simple interest and the compound interest do not join the points. And then we're just going to take a look at how they compare. But we should know now from what I've mentioned a couple of times already that when I graph the simple interest, I'm going to get a line, a linear function. When I graph the compound interest, I'm going to get an exponential curve, which means it's going to grow more quickly, okay, as time passes or the x values are increasing. So that's what we're going to take a look at here. So, okay, I will do the linear function or the simple interest as red, and I will do the compound interest in blue, or the exponential in blue. Okay, so here we go. So I start time 0. Okay, both situations we're starting with $5,000. Okay, so start at $5,000, which is right there. At year 1, 5,450. So I just have to determine what the scale is on the x-axis. So it looks like 2,468. So we're going up by $200. So year 1 is 5,000 to 450. Okay, so right about there. Okay, I'll be as accurate as I can. Year 2, 5,900. So 5,900. Okay, right about there. Year 3 is just about 6,400. So 2,4. So just about 6,400. Year 4 is 68. Okay, so year 4 is right there at 68. Year 5, 7,250, so just above 7,200. Year 6 is 77, so 2,468, so 77, right there. Year 7 is 8,150, so 8,150, okay, approximately there. And year 8 is 86, so 246, 8,600. So there you can see pretty linear, pretty straight line, and that was the simple interest. Okay, now when I go and do compound interest, and again, I'm just taking all these values from the charts on the last 2 pages that I calculated, we start in the same place. Okay, so that blue data point will go right over top of the red at time 0, $5,000 initial investment. Now, the year 1, 5,450, okay, same amount, okay, after year 1. But year 2, you notice it starts to separate just a little bit, 5,940.50 cents. Year 3, 64, and just above that. So now there's a little gap between the linear and the exponential. Year 4, now I'm just over 7,000. Okay, so that gap between the years now, every data point is going to start to increase. Year 5 is just about 77. So 2,468, so just about 77 right there. Year 6 is almost 84, so 2,4. Year 7 is almost 9,200. Okay, is almost 9,200. And Year 8 is 996281. Okay, so we are at 99, so up here. Okay, so like I said, in general, okay, what's occurring there, okay, if you're having trouble seeing those points because we haven't joined them, okay, is the following, right? The linear, okay, they're both starting at 5,000 here. The linear is doing this, like so, okay, and the exponential will be doing this, starting in the same point, very close, and then it takes off up in this direction, exponential versus linear, okay, compound versus simple interest. So part G says the graph shows that the simple interest takes on a linear pattern, okay, which is what we saw, and the compound interest growing more quickly is growing exponentially. So write the formula for the exponential function shown on the grid in the exponential form. Okay, so on the grid, that graph would have the equation of y is equal to 5,000. There's my initial amount, 1.09, right? 1 plus the interest rate, and then to the exponent of n. Okay, so there's the equation of our function on the grid. Okay, turn the page. Now, on the next page, there are some important terms that we need to understand when we're studying compound interest. Okay, and it refers to the following if I go right down to that compound interest formula. Okay, I and n are the two variables that usually give us a little bit of trouble in the equation. A and P are usually pretty straightforward, but it's I and N that are sometimes really tricky. Okay, and these 2 points right here, we want to make sure that we understand. I is not always the annual interest rate, and N is not always the number of years. So what I'm going to take a look at, and I'll refer to those I and N variables quite often in these questions, is how often your interest is being calculated. Okay, and I will refer to that and make sure that we are crystal clear on that as we move forward. So in this question, the first one, it says $1,000 is invested for 5 years at an annual interest rate of 6%. So you get 6% for the whole year. I'm investing $1,000, and the term is going to be 5 years. Okay, so there's some important information in the first sentence. Complete the table to calculate the final investment if the interest is compounded, which means, taken in, or you're calculating it, to the period of time given in the table. And you can see we have annually, which means once a year, semi-annually, twice a year, or every 6 months, quarterly, 4 times a year, or every 3 months, and then monthly, 12 times a year, or every month. Okay, so that's going to determine I and N. That's going to change those values. So annually, the first one, pretty straightforward. Okay, it says the number of compounding periods per year. Well, annually means 1 a year. The total number of compounding periods would be 5. Okay, why 5? Well, once a year, and I've invested the money for 5 years. So 1 a year for 5 years, that's 5 times I'm going to be calculating interest. The interest rate every time I collect interest is 6% because I'm only doing it once a year, and the bank has given me 6% per year. So it's still 6%. So my formula will be $1,000, and then 1 plus the 6%, 1.06, to the exponent of 5, okay? And that's the number of interest compounding periods. So when I do that calculation, again, 1.06 to the exponent of 5 first, times the $1,000, okay? And that will give me a total of $1,338.23. Okay, now we move on to semi-annually. So the number of periods per year, well, semi-annual means twice a year. So every 6 months, you're going to basically collect interest. So that's 2 times in 1 year, and I'm investing for 5 years. So that would mean I'm going to collect interest 10 times in 5 years. 2 times the first year, 2 times the second year, 2 times the third year, 2 times the fourth year, and 2 times in the 5th year. That's a total of 10 times. Now, every time I collect interest, they're not going to give me 6%. They're giving me 6% for the full year. So what you have to do is take the 6% and divide it by 2, okay, which gives you 3%, right? 3% every 6 months. So that changes my formula now, okay? My investment is still $1,000, but now the 1 plus I is going to be 1.03, and the number of interest periods is 10. Okay, so that's what I was talking about. This value of I and the value of N, okay, are going to be changing quite often. So when I do that calculation, 1.03 to the exponent of 10, and then multiply by the $1,000, that's $1,343.23. So what you can see is the more often I calculate interest, the greater my final amount will be. Okay, quarterly, like we'd mentioned, quarterly means 4 times a year or every 3 months. So if I'm calculating interest 4 times a year for 5 years, that means I will have 20 total times I'm collecting or compounding interest. Okay, 4 times every year for 5 years, that's 20. Again, my interest rate, they're giving me 6% for the full year, but I'm collecting interest 4 times a year, so I got to divide that by 4, and that will be 1.5% or 0.015. So when I do my calculation, it's going to be 1,000, 1 plus, and then 0.15, and then now to the exponent of 20. Okay, so again, 1.015 to the exponent of 20 times 1,000. This will give me a total of $1,346.86. And then lastly, monthly. Okay, so monthly means 12 times in a year. And I'm doing this for 5 years, so 12 times 5, that will give me a total of 60 times I'm going to be collecting or compounding interest. Again, they're giving me 6% for the full year, but I have to know how much I'm getting every time I collect interest or compound it. So I divide it by 12, and that's going to be 0.5%, so 0.005. Okay. So my formula will look like this: 1,000, 1.005, and then to the exponent of 60. So 1.005 to the exponent of 60, that value then times $1,000 for a final amount of $1,348.85. Okay, so hopefully those values of I and N, you understand them a little bit better in terms of how we calculate them. So you'll see in the next couple of questions what I do, or what the book does, and I recommend doing this moving forward, is you always just list those variables on the side, all the variables in the equation, fill in what you know, and then the variable obviously you don't know is what you're looking for in the question. Sometimes it's really easy to tell from the write-up of the question, sometimes not so easy, but we'll discuss that obviously as we go through the questions here. So first one reads like this: $7,000 is invested in a 6-year GIC compounded quarterly at a rate of 5% per annum. Determine the value of the investment at the end of the term. So again, what's important here? Well, I'm investing $7,000. That's going to be my principal amount. Okay, what I'm starting with. I'm putting it in a 6-year GIC. Okay, so 6 years, that's going to be the length of time. I'm compounding quarterly. So again, what does that mean? That means 4 times a year or every 3 months. And the bank is giving me 5% for each year. So they want the value of the investment at the end. That means they're looking for this, the final amount. So what do I do for I and N? Well, again, some people will go right to N because it's a little bit easier. N is going to be what? Quarterly is 4 times a year for 6 years. So I'm going to have 24 times that I'm collecting or compounding interest. My amount of interest, well, I'm getting 5% a year, but I'm basically compounding it quarterly. So I have to take 5% and divide it by 4. So when I take 5% and divide it by 4, that's going to give me 0.0125 as the interest rate every time that I collect interest. If you need to, write that on the side here, 5% divided by 4. Okay, that's how I got this calculation here. And this was 6 years times 4 times a year. That gives me the 24. So at this point, all I do is I take my equation, A is equal to P, 1 plus I to the exponent of N, and fill in what I know. Okay, I'm looking for A. P is 7,000. This will be 1 plus I, so this will be 1.0125, and then to the exponent of 24. So pretty straightforward calculation, 1.0125 to the exponent of 24, and then times 7,000. Okay, so this gives me a total of $9,431.46. And there's the total amount of the investment after 6 years. Okay, next. Christine invested $2,500 for 4 years compounded semi-annually and received $843.26 in interest. What was the annual rate of interest? So based on the question, what's the annual rate of interest? This is what they're after, right? They're after I, the interest rate. The principal amount, okay, is what she started with. So she initially invested $2,500. Now her final amount is going to be that $2,500 plus the amount of interest that she receives. So you're going to have to go $2,500 plus the $843.26. So the final amount in this question ends up being $3,343.26. Okay, the initial investment plus the interest that she received. Now N, what are we going to do for N? Well, 4 years and semi-annually. So twice a year for 4 years. That's going to be 8 interest periods. Okay, so now, again, go to your equation. A is equal to P. 1 plus I to the exponent of N. I know the final amount this time, $3,343.26. That's A. The principal amount, $2,500. 1 plus I can't do anything there because I'm after I, but to the exponent of 8. Okay, so what I'm going to do first to both sides of this equation is divide by 2,500. Okay, I want to get rid of that 2,500. So I take the final amount, $3,343.26, and I'm going to divide it by 2,500. So that gives me a value of 1.337, etc. Okay, I don't round that value. I'm going to keep that whole value in my calculator. I only round at the very end of the question. So now I have this. 1.337, etc. equals 1 plus I to the exponent of 8. Remember, I'm after I, so the next thing I have to get rid of in this equation is this exponent of 8. So either I take the 8th root of each side of the equation, or I raise each side of the equation to an exponent of 1 over 8. Whatever you want to do, however you see it more clearly in your mind, then please do that. So take the 8th root of each side of the equation, or raise each side of the equation to an exponent of 1 over 8. Okay, so when I do that, okay, I'm going to go 8 math of the answer. Okay, and I'm going to get 1.037, and again, etc. now equals 1 plus I. Okay, that's what happens when I take the 8th root of each side of the equation. Now from there, I want I, so I'm going to subtract 1 from each side of the equation. That'll leave me with 0.037, etc. equals I. Now, at this point, okay, a lot of people are very happy with themselves. They've solved for I, okay? They're very happy. But remember, okay, what have I just done? I've solved for an interest rate, but I've solved for a semi-annual interest rate. The question asks for the annual interest rate. So if 0.037 is the semi-annual interest rate, I'm going to have to take that and multiply it by 2 to get the annual interest rate. So if I take that and multiply by 2, I am going to get 0.074, etc. equals I. Okay, so that's the annual interest rate. Okay, that's what I'm after. So as a percentage, that is going to be 7.4%, and that's your final answer there. Okay, moving on. Barbara invests $8,000 in an account which pays compound interest of 6% per annum, compounded monthly. How long would it take, okay, and here's a key phrase, in years and months for her investment to double in value? Okay, so she's going to put $8,000 in an account. So that's going to be her principal amount, what she starts with. They want the amount to double. Okay, I circled that at the end. So that means the final amount will be $16,000. Okay. Now, they are giving her 6% per annum, so 6% for the year, but it's compounded monthly. Okay, so what that means is you're going to take the 6% and divide it by 12. Okay, 6% for the year, compounded monthly. I'm going to divide it by 12. That's going to give me my value for I, and that's going to come out to be 0.005. That's going to be my value of I. N, I don't know. That's what I'm looking for. So again, I go to my equation. A is equal to P. 1 plus I to the exponent of N. The final amount is going to be 16,000, double what the initial investment was, which is $8,000. This is going to be 1.005, 1 plus that I value. I'm after N. So again, same as the last equation. First thing I want to do is get rid of the a value, or what's in front of the expression with the exponent. So I'm going to go 16,000 divided by 8,000. That's going to be 2. So I now have 2 equals 1.005 to the exponent of n. Okay, so from here, you have 2 options. Either I convert this into log form, okay, or I use laws of logarithms to basically solve for n. So if I use laws of logarithms, remember I'm going to go log 2 equals the n comes down in front, and then the log of 1.005. And then to isolate n, it's going to basically look like this: the log or logarithm of 2 divided by the logarithm of 1.005. Okay, that isolates n. So since those are both base 10, okay, I can use my calculator. So log 2 divided by the log of 1.005, okay, and I get 138.97, etc. is equal to n. Now, that is, since I'm over 138, that's going to be 139, and that's months. Now, the question says in months and years. So what do I do here? Well, I'm going to basically take 139 months and divide it by 12, because there are 12 months in a year. So when I take that answer, 139, and divide by 12, okay, you're going to get 11.583 repeating. Well, that means 11 full years. Okay, if I have 11 years, 11 times 12 is 132. So I've used up 132 of the 139 months, and that means there are 7 months, okay, extra left over. Okay, so I took the 139, divided it by 12. That gave me 11.58, which means 11 full years, and the 0.58, okay, is the extra 7 months. So 11 years, 7 months it takes, okay, for her investment to double. Okay, last question for today. Borrowing money. When an amount of money is borrowed, interest is charged for the use of that money for a certain fixed period of time. If the loan is paid off in one payment at the end of the loan period, then the compound interest formula can be used. If repayments are made on a regular basis, the compound interest formula cannot be used. Okay, so obviously we're going to take a look at questions where the payment at the end of the loan, then we're going to be able to use the compound interest formula, okay, because we're going to pay it off at one time. Andrea borrows $7,500 from her parents to buy a new car. Her parents charge her interest at a rate of 4% PA, again per annum, for the year, compounded quarterly. When she pays off the loan, she has to pay $785 in interest. What was the length of the loan? Okay, so this time they're not nice to me, so I'm going to write the variables on the side, A, P, I, and N, and I'm just going to fill them in on my own. So the principal amount, what she borrows, is $7,500. When she pays back the final amount, it's going to be the $7,500 that she borrowed plus the additional $785 in interest. Okay, that's going to give you $8,285. Okay, so hopefully we're okay with those amounts. They want to know the length of the loan. Okay, so that's N. So we don't know N, or that's our question mark. And what's I going to be? Well, they're giving her 4% a year, but it's compounded quarterly. So you divide that by 4, don't you? So 4% divided by 4, okay, that's 1%. So 0.01. So again, to your formula, A is equal to P, 1 plus I to the exponent of N. Your final amount, 8,285, equals 7,500. 1.01 to the exponent of n. Okay, so again, divide both sides of the equation by 7,500. So 8,285 divided by 7,500. So this will give you 1.104. Okay, etc. I keep that whole value in my calculator. I do not round. Okay, until the end of the question. Now I can use logarithms to isolate n, or solve for n. So it'll be the log of that 1.104, etc., which will equal n log of 1.01. So the logarithm of 1.104, okay, that whole value, the log of that whole value divided by the log of 1.01 will equal n. So I have to do that calculation, okay? So log of my answer divided by the log of 1.01, okay, and that gives you 10, okay? So 10.00, okay, so that's going to be 10, but that's 10 what? That's 10 quarters, right? Because we are compounding it quarterly. So that's 10 quarters. So if I have 10 quarters, okay, that is the same as 2.5 years, okay? Because if you think about it, 4 quarters make up 1 year, another 4 quarters make up another year, and then I'm left with 2 quarters, which is a half. So 2.5 years is the length of the loan, okay? How long it takes her to pay it off. All right, so that's your lesson on finances, simple interest and compound interest. Again, remember, compound interest is basically your exponential equation, y equals ab to the exponent of x. That's why it produces an exponential graph. And when you are taking a look at the word